Okay, so we have this gear system. We're gonna label the gears. It's gonna be 2, 3, 4, and 5. And it's given that the torque of shaft A here in gear 2 is 2500 pound-inch, and it's rotating at 1200 RPMs. Okay, if you look at the side view, I'm gonna label them, and front view, you'll notice that shaft A has been moved from its original position. So if we were looking at the real front view, you would see that shaft A is behind shaft B. Okay, because the side view is the left side of the front view. Okay, that's going to be important for the 3D schematics that I'm going to draw. All right, so the first thing is to see that this is the interaction between 2 and 3. Let me redo that. Okay, doesn't work. 2 and 3. If 2 is rotating in this direction, then 3 is rotating in that direction, which means that 2 feels force coming down from the teeth of 3, and then 3 feels the force coming up, so that it's actually moving in that direction. Okay, this would be labeled W3 tangential, W2 tangential, and they're both equal. Okay, because they're reaction forces, action and reaction. Now if I did the front view of 3, or the back view of 3, where it's actually touching gear 2, we would see same lines, same angle, but from the back. Okay, so I would still see that W3T as a tangential force. Okay, I'm going to use different colors for the other ones. There is a component in the axial direction, the axis of the gear. Sorry, that would be W3 axial, and so we have those two components because this has to be perpendicular to the teeth, so it has to form a 90-degree angle here. And then because there's an angle of a pressure angle, the dashed blue line is not the actual vector, total vector, but it's actually coming out of the page of your screen. Okay, so it's like in 3D going into the page, and then the angle that it's formed between the 3D vector and the dashed line on the page, on the sheet of paper or your monitor, is the pressure angle. Okay, so just for reference, this angle is the same as this angle, which is psi, and then the angle between the 3D vector and the dashed line would be the pressure angle, phi. Right? Okay, so let's work on this. I know that the torque is the resulting value from multiplying a tangential force times the radius. Okay, so this radius dashed times this vector will give me a torque. So W2T is the torque over radius 2, which would be 2500 over the radius. And so if the diameter is 4, radius is 2. Now I know that these are diameters, these values. I'm gonna make them very clear. I'm gonna use green. 4, 8, 20, 24. I know that those are diameters because this 16 would result from adding half of 24 here, 12, and half of 8 here, 4. So 12 plus 4 equals this 16. So I know that those are diameters. And so if this is the diameter, 4 is the diameter of 2, then I have a 2 as the radius of 2. Okay. And so this is the tangential force, meaning that the tangential force on gear 3 is also 1250 pounds, right? I can get some of these components. So let's do a 3D drawing of how this looks like. I'll try to do it right above the diagram so that you can see, compare it. So I would have shaft B. Let's see if I can get it right. Nope. Okay, whatever. So shaft B, I would have gear 4 right here, and then keeps going to gear 3. Okay. So this is D, this is C, this is, it's not a good drawing. This would be gear 4, so he's going to put a tiny 4 here and a 3 here. Okay, so why am I doing it like this? Because of what I said at the beginning. A is actually behind CD. Shaft A is behind shaft B when I see the real diagram for the front view. Okay? If this is the left side, I know that A is behind B. Okay? So 2, this interaction from these vectors in blue and red and black, and 3 is coming from behind 3. Okay, so this still looks like this. It's just a spur gear, and 2 would be here. Okay, I'm not gonna leave that there, but 2 would be behind 3. Okay, so that's why this is C and this is D. Okay, all right, so if I look at those forces, I'm gonna see here the tangential force, and I'm gonna see the axial force, okay, and I'm gonna build this 3D view. Basically, what I said, or what I drew before, this would be the dashed blue line that we see under the 3D vector, and then coming out of that plane, there's gonna be an angle of pressure. Okay. So that 3D blue vector would come from here to here. Okay, forming this angle, phi. Right? So from that, I can say that the red one, I'm going to use the colors. I'm going to try to keep this consistent. Sorry. So the red one, W3A, is going to be equal to the tangential one times tangent of psi. Okay. You can look at that here, down here to the right, this angle, which is phi. If you want the opposite and you have the adjacent, you do the adjacent times tangent of the angle to get the axial one. And I can just label this. I'm going to label the dashed blue line. So if I have this as whatever, mn would be equal to W3 tangential over cosine of psi. Okay, because the dashed blue line is the adjacent and the hypotenuse, and then W3T is the adjacent. Okay, I'm gonna draw this just once and I'm gonna delete it in just a second. Tangential and hypotenuse, and the angle that is formed between those two is psi. Okay. And I also know that the radial force, I'm going to add here as green, coming into the gear in a radial direction, would be equal to mn times tangent of phi, right? Because this triangle, again, I'm going to delete it in just a second. 1, 2, 3. That's the angle that it's formed, and the opposite is what I want, and what I have is the adjacent. Okay, so that's tangent. Okay, so basically this is just equal to W3 tangential tangent of phi over cosine of psi. Right? I'm going to give some values to this. The axial one would just be W3T tangential tangent of 30 in my 30, 60 special triangle. This is 1, this is 2, the square root of 3. So this is just going to be 1250. And tangent of 30 would be 1 over square root of 3. And W3R, the radial one, would be 3 tangent of 20, which is the pressure angle over cosine of 30. And this is 525.34 pounds. Okay. Right. Now, if I draw this same shaft from the side, so from the positive x, I'm going to give some values to this, z and y. So if I do the zy plane from the positive x, what I would see is gear 4 and gear 3 behind it. No. Okay. Did work. Gear 3 behind it. I know that this force tangential on 3 looks like this. Okay, and I know if I look at the 3D or the front and side views, I know that gear 5 is touching gear 4 at the top. Okay, so if I look at this here, here, then I would see gear 5, okay, touching gear 4. I'm not going to keep it there, but what I'm saying is there's going to be an interaction force at this point, at the top of gear 4. So there's going to be a tangential force there. Okay, tangential force is going to happen here, and it's going to go left. Why does it need to go left? Because I know that the sum of torques, I keep going back to that, sum of torque, which is the inertia times the angular velocity, okay, has to be equal to, this is 4 and this is 3. On shaft B, okay, which is that shaft that has 3 and 4, the torque of 3 plus the torque of 4 has to be equal to 0. Okay, angular acceleration is 0. The shaft is not moving quicker or slower over time. There's no acceleration, so it means that the torques have to be 0. And then 3 would be negative because it's clockwise, and then 4 would be positive because it's counterclockwise. So basically all I'm saying is T3 is equal to T4, or that W3T times radius of 3, which is this distance to the center, has to be equal to W4T, which is this. Okay, times radius of 4, which is this distance. Right? From that, I just know that W4T is equal to R3 over R4 times W3T. Radius of 3 is 10. Radius of 4 is 4. Sorry, 10 and 4, yeah. So 10 over 4 times the tangential. This is 5 over 2 times 625 times the same. So 50 divided by 2, 5 times 625, and this is 3125 pounds. Right? So I already have all of these. I'm gonna draw that here in the 3D. This is W4T, and the last one that I'm missing here, I'm gonna use a different color, purple. There's gonna be a component in the axial direction because this is per gear, so it's also at an angle of phi. Okay, so if I want to go to my opposite from my adjacent, which is the yellow one, from this I can also know that 4 radial is 4t times tangent of phi. Right? And that is equal to 11374 pounds force. Okay, so I have purple, I have yellow, and I have the green one, the black one that we kind of don't see here. It goes all the way down to this point in the back, which is the tangential one. So let's write those there. Green would be W3 radial, and red would be W3 axial. And we have all of those, all 5 vectors, which is everything we need. So why is that everything we need? Because for the reaction forces and for the shaft itself, the reaction forces at the bearings, D and C, okay, that these cannot move. I'm gonna do a sum of forces in the Z and the Y plane, ZX and YX plane. So let's start with the YX. Okay, so if I'm looking at this being X, this being Y, I'm gonna have some forces coming. It's like looking at this 3D drawing from the positive Z axis. Okay, so from the positive Z axis, I would see that this is D, that this is C, and that there are some forces at gear 3 and gear 4 locations. So at gear 3, I would see the black vector coming up, W3T. And at gear 4, I would see a purple vector coming down, which is W4 radian. And I know those values. I already have all those 5 values. Okay. The other thing that I need is the distances. So the distance from C to gear 4 is 3, and the distance from gear 3 to D is 2. Okay, so basically what I have here, if this is in the shot, is a 2, a 3, and then the difference between those, if they add up to 11, this would be a 6. Okay, so why are those important? Because I'm going to do a sum of forces about D, sum of moments about D. I'm going to have positive 2 times W3T, which was the 1250, minus 8, because that would be counterclockwise, the purple one, which is what I just found at the end, 1137.4, and I don't want to move this. Yeah, let me start over. So sum of, I'm gonna move this just for a bit. It's gonna be positive 2 times 1250 minus 8 times the one that I just found, 1137.4, and then I'm only seeing that this value, this negative value 8 times 1000 is gonna be higher than this. I'm gonna assume that this is also going up, that my C Y is going up. So at a distance of 11, I'm going to have Cy, and that has to be equal to 0 because this whole shaft is not rotating about D. Okay, so from this, Cy is going to be almost exactly 600 pounds forces. And then if I do a sum of forces in the Y direction, I'm going to have, I know that this is kind of 600, this is 1250, this is 11374. So just by looking at these values, I know that the reaction force at D should be negative. I'm just gonna, for now I'm not gonna draw it, but I'm just gonna say dy, reaction at D, plus W3T positive minus W4R negative plus Cy has to be equal to 0. Okay, so I have all these 3 values except dy. Dy turns out to be minus 712.6 pounds. Okay, that means that there's a force coming down called dy of 712.6. Right, and that is all I need to do a shear diagram. Okay, x, v. I'm gonna go down 712. I'm gonna come up 1250. I'm gonna go down 1137, just a little bit lower than that, and then here I'm gonna go up 600. I know that this is a 600, and I know that this is a 712.6 negative. Okay, I don't need the other values because what I care about is the moments for the shaft, right? So this is a negative slope of 712, a positive slope of I don't know how much, but then another negative slope of 600 that brings it back down to 0. So this value right here is going to be 2, this distance, times 712, but that's smaller, so I'm going to write it down, but I'm probably not going to use it. Okay, it's going to be smaller than this 600 times 3, which is this distance, which is 1800 pounds inch. Now I don't know which one I'm going to use because this is just one of the components, the Y component. Okay, but at least it's a starting point. Now I'm going to do the exact same, but not in the Y X plane. I'm not going to do that. I'm going to do the XZ plane. So looking at it from the top, from the positive Y I'm gonna see the green vector and the yellow vector, right? So remember that. I'm gonna draw D to C from left to right, looking at it from the top. At gear 3, I'm gonna find the green vector, and at gear 4, I'm gonna find the yellow vector. Basically, I'm just gonna repeat this, but for the Z instead of the Y. Okay, so what I just said is D on the left, C on the right, this being the X, this being the Z. Okay, looking down at it, I'm gonna have the green vector. I don't know if I use the colors. Let's use the colors. The green vector, W3R, which is equal to 5, 25, 34 from before. I'm going to have the yellow vector at the gear 4, W4T equals to 3125, also from before. And I'm going to have some reaction forces. From the same process I did before, sum of moments about D. I have this 2, this 6 up to here, and then this 3. And I have 2 times 5, 25, 34 positive. Then a negative 8 times 3, 1, 2, 5. And then at C, again, this value, the second value is much higher, so I'm assuming that C is going to go up. Okay, C, in this case, Z is in the Z direction, that reaction force at C at the Z direction, plus 11, which is the distance CZ, 0. This gives me that ZZ is 2177 pound force. And sum of forces in the Z direction, in this case, I'm going to have, so this is 2177, I'm going to have that one, CZ plus W3R minus W4T, and again I'm just going to assume that DZ positive, and this has to be equal to 0. Since I have these three values, I solve for DZ, and this gives me 422.66 pounds force. Okay, also positive. So here I have DZ equal to 422.66. Now I move forward with my shear diagram. Okay, so shear in Z. I start at 0, go up 422.66, go up another 525. I don't know what that value is and I don't care about it. Then when I reach this, I'm gonna go down 3,000 something, so that's quite a jump. And then here, go up 2,000 and something. Okay, to 177. Those values I do know, and this would be negative. And then I use that to do my bending moment diagram. Okay, so a slope of 422, a higher slope of something, 500 plus 400, and then going down to this point. So this point where gear 4 is what I'm interested in. That would be equal to this 3 distance times this force. This value is just that area, which is 3 times 2, 177, which is equal to 6531 pound inches. Pound inches. Okay, so what I was saying before is I didn't know if it was a gear 3 or a gear 4 that I'm going to have the maximum moment. That's what I didn't know up to this point. I don't know if I was going to use this value that I didn't calculate or this value 18, because even though 1800 is higher than this value down here, I don't know if the value from the other moment diagram was going to be higher here at gear 3. It turns out it isn't. The highest is not at gear 3, it's at gear 4. Okay, so what I do with these two, 6500 and 1800, is come up with the overall moment at gear 4. Okay, and that would just be, with Pythagoras, 6531 squared plus 1800 squared. Okay, and that is 6774.5 pound inches. Okay, and why was I interested in this? Because that's what the shaft is feeling as a moment. Okay, so that moment 4 that I just calculated is the maximum moment inside shaft B. Maximum moment inside shaft B, which goes from bearing D to bearing C, occurs at 4, what gear 4 is, and is equal to this value, M4. Okay. This is going to be the alternating moment. What is the mean moment? It's going to be 0, because I don't know the direction of this. It's somewhere between the positive C-axis and the positive Y-axis. So somewhere between this line and this line. I don't know what angle, but it's at a specific angle. Anywhere on the surface of the shaft, I'm gonna feel this moment, sometimes positive, sometimes negative. Okay, so it's under compression and tension. So in average, the mean moment is gonna be 0. But also, I have that the alternating torque is 0. Okay, because it's not alternating, it's a constant torque. Shaft B is under the torques that I had already calculated here. Okay, T3 and T4 are equal and in opposite direction, so the torque inside shaft B is either one of these. Okay, so let's do R3, which was the 10 here. Okay, so 10 times WT3, which is the 1250. So this is 12,500 pound inches of torque, and that is constant. It's never changing. It's not alternating. That's what I'm saying here. The mean torque is 12,500. Okay. Now, how do I use this? Yeah, there's going to be a little bit of compression and tension depending on which section of the shaft you're looking at. Yeah, we'll get that to in just a second, but it's not going to make a huge difference. So how do I use this? I go to whatever failure criteria I want to use. So let's say Goodman. I know that that shaft is under fatigue, and I have these values. And if you remember from the book, you have a capital A that was something like this. Okay, I have an A squared and 3 shearing at KFS, TA squared. And then B would be the same, but with mean moment and mean torques, right? I am not taking into account any stress concentration because there's no fillets, there's no change in radii. So I only have these values, and I do have from what I just wrote here all of those four values to get my A and my B coefficients and put it in the Goodman equation for either calculating the factor of safety n, or in this case, since I wasn't given a diameter, I can just calculate the diameter so that the factor of safety is something that I want. Okay. A as C, B as UT. B, you compare them to the mean values that are not changing, so SUT, and the alternating ones, A, TA, and MA, you compare them to SE, which is the endurance limit, which is what has to do with the fatigue. So these you can calculate from the material that you give. You can find SUT, you can calculate the marine factors for SE. You already have A and B based on everything that we just did, and then you can select the factor of safety of 2 or something so that you know what your D, diameter of the shaft, is. Okay, and we're done with the shaft. Now let's look at the bearings. For the bearings, I am going to use these values from the let me choose a different color. From the let's do orange. Shear diagrams, sorry. So these reaction forces, for example, for 22 and 712, right? Those two values are affecting D. Okay, would be this. So in orange, the D. Let me draw those here. I have a dy and dz in this direction. So there's an overall d vector that I can calculate as square root of dz squared plus dy squared. Okay, and that value would be 828.5 pounds. Okay, now let's do pink. At C, I have a cy coming up. So cy coming up, and in the z plane, I have a zz coming in the negative direction of z, 2177 zz, again creating an overall vector in this direction, c. Okay, that c would just be c would be cz squared plus cy squared, which gives me a value of 2258.4 pound force. Right? These are the ones that I'm going to use for each bearing separately. Okay, so at my bearings, I have a bearing D. Let's do C first, so that I don't have to change the color yet. C, that has a force. So I just want to make sure. Yeah, a force that looks something like this, going into the center of the bearing, and is equal to 2258.4 pound forces. This would be the radial force for this bearing. Okay, and then I also have a bearing D at the other end. Okay, that has a vector coming down in this direction. D equal to 828.5 pound force. Okay, and this is also the radial force for that bearing. We have two different problems here, one for D, one for C, and I only have the radial force for now, but I also know that it's under thrust. There's an axial load affecting both of them. I'm gonna add this just so that you know where these were coming from. Okay, there was a component in the Z and one in the Y, and it ended up being a force going into the center, which is a radial force. Okay, same with the other one. There was a component in the Y, there was a component in the Z. Okay, and that's why we have this vector coming in towards the center of the bearing, and that's why it's also a radial force. Okay, so last thing, we have the only vector that we haven't used so far. My 3D image here is the red one. This red one is what's causing the axial or the thrust on the axial load or the thrust on shaft B, lowercase b. Okay, so if I draw shaft B on the x-axis, let's do it close to this because I'm going to use it for both. Okay, where this is D and this is C, I have a force right here going towards the left, which is where gear 3 is located, and this force is equal to W3 axial. Right? What I know about those is that D and C are not going to move. They're bearings. So the shaft cannot move in the X direction, left or right. The X direction, left or right. Okay. What I know is that the deflection at point 3 from D has to be equal to the deflection of point 3 from C. Okay. And knowing that this is just going to be the deflection of compression and tension, PL over AE. Okay. The force that goes inside the section from 3 to D is going to be dx. Okay, we already had dy and dz to get the total d going towards the center of the gear, which is the radial force. Now we have this dx, which is in the x direction, which is in the axial direction of the bearing. Okay, so PL was this distance of 2 from here to here over AE, and it has to be equal to CX, which is the force between 3 and C in the X direction, times this distance of 9 from gear 3 to bearing C over AE. The cross-section area is the same because it's the same diameter and it's the same material, so I don't care what the elastic modulus is. All I care is that 2dx is equal to 9cx, meaning that 2/9 of dx is equal to cx. But I also know that cx plus dx is equal to what? This comes from the sum of forces in the x direction. Cx plus dx minus 3a has to be equal to 0. Okay. So if Cx, which is 2/9 of dx plus dx is equal to W3a, which was the 1250 over square root of 3, I get that dx is 590.5 and that Cx is equal to 131.2 pound force. Okay, why do I care about those two? Because those two, Cx and dx in the x direction, are the axial forces. Okay, so for C, x 131.2 pounds, this is the axial force of that bearing. And then for D, dx, which is the 590.5 that I just calculated, is the axial force for this bearing. Okay, what do you do with those? You combine them. You do the whole axial over C0 to see if to go into the table to calculate an E, to see if the FA over VFR is higher than E, and then use the equation to combine these into an equivalent load, so that you can look up a force, a rated force, and compare it to what the catalog number gives you, right? And then you're done, because we already know what kind of bearing C should be when we get this equivalent force here, what bearing D I should select when I get this equivalent force for that one, D, and I know what the diameter of the shaft should be. I already solved everything that we needed for shaft B and bearings CD. Okay.